Hello everyone, I'm Neda Meibodi and I'm presenting a model of selection history in visual attention. Selective visual attention is a brain function that filters irrelevant sensory inputs to focus on relevant items, and it is traditionally known as an interaction between bottom-up and top-down mechanisms. Later selection history is proposed, and it is known as the third category of attention guidance. Selection history comes to play when an object is emphasized because of previous attentional deployments in the same context, and it includes different phenomena such as learning, priming, and also reward-based bias. To show how bottom-up, top-down, and selection history work together to guide visual attention toward a specific target, we presented an algorithmic model. We call this model algorithmic in sense of MAR, and the model connects visual stimuli to human behavior. By selection history here, we mean the effect of learning from previous experience on the current task. The behavioral data of the first experiment that was proposed by Feldmann and others is used for modeling. The experiment was a psychophysical experiment with recording of responses, reaction times, and EEG. In this experiment, an associative learning task was combined with a visual search task. As you see here in these examples, in all tasks, there is a fixation point on a screen and 8 different elements around the fixation points. Experiment has two types of tasks, learning and search. In learning tasks, color or shape had to be categorized based on participants' group membership. In search task, the orientation of the line in the diamond had to be reported. In half of the trial, there is a red distractor available. Participants were randomly divided into two groups, color group and shape group. In learning tasks, participants in color group had to categorize the color singleton, blue versus green, and participants in shape group had to respond to the shape singleton, triangle versus pentagon. Participants with the left hand pressed one of two buttons placed on the left side of the response pad. In search tasks, all participants reported the orientation of the line in the diamond, horizontal or vertical. Participants with right hand pressed one of two buttons on the right side of the pad. If the responses were incorrect, participants received beep sounds as feedback. The experiment was done in two phases, practice phase and main phase. In practice phase, participants had to learn on a trial and error basis that either color or shape was the response to relevance. In main phase, participants performed both tasks, learning and search, in random orders, as you see here in this example. The assumption was that the learning experience should affect attention deployment in the search task, and also a between group difference in attention deployment was expected to shape target and color distractor. The experimental results showed participants in the color group got distracted by color distractors in the search task much more than participants who had learned about the shape. Both reaction time analysis and EEG results indicated an attentional bias. As you see here for search task, the mean of the reaction times for distracted present tasks in color group is higher than the mean of the reaction times for the same tasks in shape group. This attention bias can neither be explained by bottom-up nor by top-down control, but is resulting from the participants' individual selection history. Reaction time database of this experiment is used in current study for modeling. As you see here, there is the schematic of our model, and the model starts by extracting features from the experiment tasks, and after taking several steps, it predicts the parameters of the reaction time distributions. By distributions here, we mean exponential Gaussian. Several probability functions were fitted on the observed data by maximizing likelihood, and the best fitted one, X-Gaussian, was selected for modeling. Why exponential Gaussian? Because reaction times are not distributed normally. Because of the line tail on the right, they might have an exponential component. X-Gaussian is a convolution of Gaussian and exponential distributions, and it has three parameters, mu, sigma, and tau. X-Gaussian has been popular recently in analyzing psychophysical data. In next slides, I go step by step through the model to see how our model works. This is the first step, when by feature extraction, feature maps are made, color map, shape map, orientation map, based on feature integration theory. The theory says in pre-attentive stage, stimulus features like color or shape are encoded in parallel. Next step is making saliency maps, and we used self-information maximization to make our saliency maps. It was proposed before in a saliency model that was called attention based on information maximization. Then later, saliency maps and history map are integrated into priority map. Integrated priority map is a theoretical framework to explain how selection history and other factors of attention guidance interact. Priority maps are linearly mapped into reaction time parameters. Here you see the weights that are actually the model's parameters. WS is saliency weights and has three components for color, shape, and orientation. And WH is history weights. WD and BD are reaction time distribution parameters and reaction time distribution biases, and each of them has three components, mu, sigma, and tau. In machine learning part of the model learns to predict the parameters of reaction time distributions, while goal-driven information in top-down manner controls the way that maps are combined into a priority map by affecting the weights. To compare how model predicted distributions are close to real distributions, we plotted them here on these examples for color group participants and shape group participants. And as you see, the model predicted one that is in green is very close to the real one and fitted well on our reaction time database. To quantify how close the model predicted distributions are to best fitted distributions, we evaluated KL divergence, and it returns very small numbers. To see how selection history or history map can affect our model, we tested three versions of the model. In first one, that is a feature that has a feature level selection history The history map contains the response-relevant features in the learning phase, blue or green for the color group, triangle and pentagon for the shape group. In second model that has a dimensional level selection history, the history map includes all color singletons for participants in color group and all shape singletons for participants in shape group. Here on the bar charts, you can see the model evidences. For model comparison, we used Laplace approximation, and we also fitted the model per participants and then per groups. And in all cases, model 1 scores the best. As you remember, we talked about the weights, WS and WH, saliency maps weights and history map weights. To see how the model learns to predict these weights and how these weights differ between color group and shape group, we plotted them here on these bar charts for both color and shape group. And then if we look at history and color map weights, we see that they are higher in color group than the ones in the shape group. Participants in color group respond to the learning tasks by relying on history and color, and also higher history weight than color weight here shows an effort on red distractor suppression in search task. Orientation map and shape map in color group. As you see, orientation map has the highest weight. By that, participant in color group responds to the search tasks, and also they ignore the irrelevant shape singletons in learning task. In shape group, the highest weight is for shape map. By that, participants in shape group solve the learning tasks, and also in search task, attention can be guided to the shape singleton, I mean the diamond, that contains the target. So shape map is response relevant in both tasks. If I want to compare the results of the experiment with the model, the experiment showed a between group difference. The model also captures between group differences by giving different weights to the maps in color and shape group. The experiment showed attentional bias to the red distractor in color group. The model also shows an attentional bias to the distractor in the color group by giving higher weight to the color map in color group, while this weight is close to 0 in shape group. So in general, this attention bias can be the result of the participants' individual selection history, and also the model shows different selection history effects between groups by giving higher weight to the history map in color group than shape group. So in conclusion, we presented a model of selection history in visual attention. The model successfully predicts the reaction time distribution parameters, and the model shows integrated priority map can be a successful framework to explain how attention mechanisms interact. We tested different versions of the model, and the model, which includes selection history, beside bottom-up and top-down control, is the best suited for describing the behavioral results or reaction time results. In our next steps, we tried to add intertrial priming effect and task switching effect to the model. And also, we will make a computational model for both ideal and non-ideal observers to know what the attentional system is trying to achieve. Thank you for your attention.